Okay, let's get started. So for those who haven't picked it up, quiz scores are up here. Feel free to pick them up. Scores were actually really good on this one. The best of all quizzes so far at let's try to zoom in here, at an average of 82. That very well done. I was very pleased with that. So what's happening on Friday? Test, awesome. So as before, the only things that will be tested are entirely all the array stuff, which is chapter 8, and from chapter 9, only the search algorithms. Even if we get to all the sorting stuff on Wednesday, it's only on the search stuff, and we'll finish the search stuff up today. So chapter 8, the main things are dealing with arrays, some of the terminology and stuff, then vector, which is obviously a lot better than array, and then working with 2D arrays, all that kind of stuff. For searching, what is a search algorithm? Linear and binary search, the trade-offs, and we'll see those today. Searching an array of objects, but that's pretty much the same dealie. Any questions about the test that's coming up on what day? Friday, good. Good. Any questions? Yeah.
In your honest opinion, what is something that we should strive for in terms of writing code? Like, which is the most important? Is it array, how to write an array, or like how to create sorting algorithm with certain key variables?
Good question. So basically, what should you be worrying about in terms of the two programming questions? Is that right?
Yes.
Okay. So how is the test broken up? So there's a section of multiple choice and then two programming questions. How many sections of chapters are there? Two. You think that's a coincidence?
No.
So think about that, but yeah. So that should try to help you a little bit. So I'm not going to ask you implement linear and binary search because you know how to do linear search, and we'll see how to do binary search today. I'm not going to ask you things that we've already done because that's not useful. What I'm going to ask you is, like the other two tests, I'm going to ask you, here's a problem that's related to these. Can you use the ideas from them to solve this problem? So it's not something entirely new, but it's based off of the things that you already know. So what's a good example? So one could be, suppose we didn't do the lab about standard deviation. So one of the questions could be implement standard deviation of a list of numbers. Instead of just like finding the sum, average, or largest, I ask you, can you find the standard deviation of this list? So that could be a reasonable question. Or so this is not going to be a question, nor is the other one. But suppose that we actually do implement linear and binary search, and then we see this amount of runtime on these data. What can you conclude from that? So things like that, being able to solve real-world problems or problems that are based off of these, using your knowledge of how we actually worked with these. So using your knowledge of these search algorithms, can you implement this search algorithm that's based off of these two ideas? Okay, so that's what I would focus on. Like, what are some small differences between what I have here and what I could ask? Yeah.
In your honest opinion, what do you think is going to be the hardest question you're going to ask? Is that too much?
What do you mean by hardest? Because that's subjective.
Okay, like in terms of coding, how long would this? How many lines?
So, a great question. So, how much code? I wouldn't guess more than 20 or 30 lines on each of the pages. So 40, 60 total at most. But related to that, the TAs told me that some people needed an extra sheet for the test 2, so I'm going to include an extra sheet for every test this time around. So the way it's going to come is the same as test 2 with the front sheet, multiple choice on the back, then programming question 2 with a back, programming question 3 with a back, and a whole nother sheet for you to use. So just in case you happen to either write big or write a lot of code, so there's not going to be a lot of code writing, but you have to think a little bit. It's not going to be some brute force type things. And that's something I would never want to ask, being able to brute force some problem. But it's being able to think a little bit about how would you apply the things that you know to solve this problem. Okay? Any other questions about the test? Yeah.
It's a general overview question. Could you show how to print out the 2D vector?
Yeah. Yeah, certainly. So, so let's open up C-line. Any other questions before I do that quickly? Yeah.
I'm a little bit confused about like when you should use parallel arrays and when you shouldn't as well.
Great. So I'll answer that quickly. So we talked about this. The reason you would want to use parallel arrays is that you're including all of the data of one type in one place. So if you have an array of names, an array of scores, for example, then you're putting all the scores together and all of the names together. And if you're not doing anything complex with the data, like sorting it or whatever, then there's no reason to use anything else other than parallel arrays. Because if you're just iterating over the data, just iterate over the indices of one, and then print the corresponding value of the first array and the second at the same time. So you don't have to do anything complex there. But if you do have to do something complex where you have to shift elements of one array around, then you have to do the same thing of the other array, which could be a nightmare to deal with. So what you would do instead is you would make a class which has both of those fields, so maybe a name and a score for each student, and then I have an array of students instead, so that when I do a sort or whatever, shift elements around of this student array, then the corresponding data goes with each other. So you don't have to handle that, yeah.
So would that look like a two-dimensional array because it has like a name and score in it? Or
But
would it actually look
it wouldn't be a 2D array because here the names and the scores are in tandem with each other, whereas a 2D array is each row has a whole bunch of columns. So it's not like one-to-one correspondence. You could, for example, do a 2D array where you have 2 columns or 2 rows. That would do exactly the same thing. So you could do a 2-dimensional approach there, but it's just parallel arrays are 2 separate arrays that you try to work with in tandem. So let's make a quick new project. I'll call it Untitled. Any other questions before I do the 2D vector example? Okay, so let's just make a 2D vector. Make sure we include the right header. It actually doesn't matter if I use a vector or if I use a 2D array. It'll work exactly the same. So let's just make a 2D vector because that's what was asked, of ints, for example. And then maybe, let's not populate it with data, but let's just assume it actually has data. So maybe populate vec with data here. And then how do we loop over this thing 2-dimensionally? Well, the issue might be, well, each of these vectors inside of the overall vector, could those have different sizes? Yeah, potentially. So what is the best way of dealing with things of different sizes? What kind of for loop would be useful for this? Range-based. So if I don't have to deal with the indices, just use a range-based for loop and make your life easy. So one way you can do it is, let's loop over the rows as the outer loop, and then for each of the rows, let's iterate over that single row. So let's do auto row in vec. So this is for every row in the vector. So each of these rows right here is going to be itself a vector. So row here is a vector because we're iterating over each element of the 2D array. But here, if we want to iterate now over each of the rows, we need to iterate over the row. So maybe we can do auto val, so maybe value. For every value in the row, then maybe we do something with value now. So just to recap, vec is a 2D array, and the way we loop over it is we go over each of the rows, so one row at a time, and then once we're looking at one row, we iterate over that single row only, okay? But if we wanted to use indices, then this might be a little bit more complicated. I wouldn't ask something like that on a test, but the way to iterate over a 2D array is something similar to this. Does that answer your question?
Yes.
Okay. Other questions about the test or this? Yeah.
So you need to use the colon?
Yeah, you do need to use colon. Yeah, because that's a way of communicating that you're using the range-based for loop. You could use indices here, but then you need the 2 semicolons with the init, update, and condition step. But yeah, for a range-based for loop, you do need the colon there. Yeah.
How would you determine the size of the outside vector and the size of
Right. So how do I find the size of a vector? Dot size. So we can actually do this quickly. So maybe we can look at the row index. So the starting index is always what? 0. And then what is the maximum that the index could be? The size of the vector. So we'll look at vec.size and then row idx plus plus. So here I'm looking at each of the row indices of the vector, and the number of indices is vec.size. But now I want to iterate over vec square bracket row idx. Since I'm not looping over the rows now, I'm looping over the indices. So the vector, the row vector itself that I am interested in is vec square bracket row idx. So let's look at the value idx, so the value index. That always starts at 0, regardless of what the vector is. But how high can the val idx go? Well, what vector am I looping over now? Vec square bracket of row idx. So I'm looking at row idx, the index of this vector. So this is the vector that I'm currently looking at, the row I'm looking at. And then so this is a vector itself. How do I know the size of this thing? How do I know the size of a vector? Dot size. So then I call dot size on this thing, and then val idx plus plus. And so now the value that I want now is vec row idx of val idx. So this is the vector of the inner for loop, and then I'm looking up the index of the value that I'm going through this for loop. You see why range-based for loops are better? So this could be quite cumbersome to write, okay? But if you really did need the index, this would be a way of doing it. Any other questions about this or the test? Okay, so let's get back into searching. So as we talked about, I think last time, we are talking now about searching through data. So we have these wonderful arrays and vectors which can hold tons of data. How do we actually find data in it? So maybe we have a list of ASU students. I got to find some student with maybe some ID. What is a way of finding some student in that list? So the two methods are linear and binary search. So linear search is nothing special. All you're doing is just go through the entire structure, vector, or array, or whatever, and then if you ever find a match, just stop and say true. If you iterate through the entire thing and never find it, return false. Okay? So in this array right here, if I search the value 29, what should I return? True. And the reason is, I look at 17, it's not there. That's not the value. Then I go to 23, not the value. 5, and then I keep going, and I finally go to 29, and I say, yep, that's the value because it's equal to the thing I'm searching for. And so I say true. What if I search 7? what should I return? False, because I look at each of the values, every single value in here, and then I find that it's not there because it wasn't equal to any of the values in here. So the great thing about linear search is it's easy to implement because, and we can do an example of this, but all you're doing is just one for loop over the entire thing, and then inside there you just do if the current value I'm looking at is equal to the thing I'm searching for, return true. If it's not, then I have to do the next value. And then after the entire for loop is done, I've looked at every value. If I haven't returned anything, I just return false. And the other great thing is that you can put the elements in any order. So it doesn't matter what the order is, you can put them in any order. The disadvantage is that it's slow because if you have 10 million elements in your array or vector, on average, you may be looking at 5 million on average. So it could be quite costly, but we're going to return to this in a few minutes. Any questions on linear search? I don't think so because this should be pretty simple. The one that's a little bit more complicated but can give us a lot of performance improvement is binary search. So if you remember the example I gave where I asked you, I'm thinking of a number between 1 and 100, and I want you to find what my number is. I tell you whether it's too high or too low. Your first guess was 50, because once I tell you whether it's too high or too low, then you can adjust your guess to half of the list. We can now ignore half of the list based on what I tell you. So that's what binary search is really good at. So assume that the list is sorted in some order, say ascending order. Then what we're going to do is at the beginning, I'm going to have 2 pointers, one at the very beginning of the list and one at the very end of the list. And what I'm going to do is examine the middle element halfway in between. If the thing I'm searching for is less than this value that I'm looking at, can it be in the second half of the list if it's sorted? No. So it must be in the first half of the list. So I'm going to have to change some of the pointers. So do I change this pointer if it's in the first half of the list? No. Do I change this pointer, the end one? Yeah, I should update it to be halfway in between. And then now I search again on this half of the list. And then maybe I search this element, maybe it's bigger than this element. So should I update this pointer or this pointer? The first one, right? Because I know it can't be in the first quarter of the list now, so it must be in the second quarter. And then I keep going. At some point, I'm just going to keep dividing by 2 until at some point, I'm going to have them around one element, and then that better be the element. If it's not, then I'm going to iterate one more time, and then the beginning pointer is going to appear after the second pointer. And then at that point, I know I'm done because I would have found it by now if the list is sorted. Okay, so this is what happens. So we're going to do an implementation of it. If the middle element has the desired value, great, we're done. If not, then we got to figure out which half of the list it actually is in. And then we're going to continue working with that portion, and then we keep going until we either find the thing or we don't find. We determine that there are no more things to search. So this list right now is just a sorted version of the earlier list. So if I am searching 11, well, the beginning pointer is at index what? 0. What is the ending index at? Well, let's see. 1, 2, 3, 4, 5. Index 6. So what is halfway between 0 and 6? 3. So I have to look at index 3. What is at index 3? 11. And so if I'm searching 11, I find it on the first step. Awesome. Whereas linear search would take 4 steps to reach there. But let's just say I'm searching 3. I'm still looking at 11 as my first guess. Is 3 less than 11? I know it's early. Yeah, it is. So I don't have to search in this half of the list. So my beginning pointer, as we just said, should stay at index 0. We've determined that. What should the second pointer be updated to? Index what? 2 or 3? How many say 3? How many say index 2? Yeah, it should be 2. Why 2? Yeah, because I already looked at 3. If I make it 3, then there's no point in actually doing that. So I have to make it updated to 2. And then I check again. What is halfway between 0 and 2? Index 1. Oh, 3 is there. Awesome. But let's just say I'm searching 4, which is not in this list. So we do halfway in between. We say, oh, 3 is not the element, but is 4 bigger than 3? Yeah, so I got to update the first or the second pointer? The first pointer. So let's see. The second pointer's on the 5 right now. First pointer was at the first index, which is index 0. 3 is at index 1. What should the first pointer be updated to? Index 1 or index 2? Index 2. Why 2? We already checked index 1. So when we're doing this halving step, we update the second pointer to halfway in between, -1. And then if we're moving the first pointer, we update it to half +1, because we've already looked at the middle element by now. So then okay, we're here. That's great. So the first pointer's at 2, and the second pointer's also at 2. So is 4 equal to 5? No. So is 4 less than 5? Yeah. So am I going to update the first pointer or the second pointer? Second one to be the middle -1. Oh, oops, what happened? The first one is now strictly the second one is strictly earlier than the first one. So they're out of order, which means what? We're done searching. Because at this point, if the value was in this thing and it is sorted, we would have found it by now, but we didn't find it. So therefore, it's not in the list. Pretty cool. So let's actually let's look at this first. So what is the benefit to this? It says here that it is much more efficient than linear search. Well, what's the justification for that? If you have n elements, the number of comparisons, I guess the math didn't show up. So can anyone figure out how many comparisons I'm going to make? Well, let's see. I'm having the list every time. So what you can figure out is we're doing a log of n number of comparisons. So if I have 1,024 elements in my list, I'm going to only do around 10 comparisons in that list. Okay, on average, because I'm having the list every time. 1,024 is 2 to the power 10, so that's where I got the 10 from. But it's going to be around the log base 2 of the number of elements in the list, because I'm cutting the list in half every single time. Okay, obviously it requires that the elements be in order. But it says here that it's much more efficient than linear search. Do you think that's actually true? Well, I hear a yes and a no. So what do you think we should do? Where what is? That could be, yeah. But it says it is much more efficient, which means every single time it's much more efficient than linear search. Either about the same or a lot faster. So let's just test it. So let's actually look over an implementation of binary search. I will post this code on the website, but this is just a demonstration of how you would implement binary search. So here's a sorted integer array of some ID numbers, and maybe that we want to find some employee ID, whether it's in the system or not in the system. So we enter the ID, and then we call binary search on this thing. And then by this we can see, oh, if it returns -1, then that means it's not in the list at all. But otherwise, it'll return the value that is found in the list because it's there. So here's how it works. So I'm going to pass in the structure that I want, the number of elements in there, which if we're passing a vector instead, I could just call .size on it. But for arrays, I have to pass the size in. And here's the value that I'm searching for. So I want to determine if value in a binary search way is in the array list or not. Okay, so I'm going to have this bool which corresponds to whether I actually found this thing or not. And then if at some point I have found the thing, I set it to true, and then I exit this while loop. But as long as I'm not finding it, and as long as the first pointer is either at the same point or earlier than the second pointer, we just keep going, having the list at every point. Well, I find the middle index right here. So I just do the first pointer plus the last one, divide by 2, find the middle index. And then if the array's value is the one that we're searching for, great, we're done. We just found the element. So we find that the position that we want is this index right here. But if not, if it's larger, then we need to move, the thing I'm searching for is less than the thing that I just found in the array, then it must be in the first half of the list, not the second. So that means I have to update the second pointer to be the middle minus 1. But in the other case is that it's in the second half of the list, meaning that I have to update the first pointer to be the middle plus 1. Okay? So that's actually the entire thing. It's relatively straightforward to implement. There's actually a small bug in here, and I invite you to figure out actually what the bug is. But yeah. Mm-hmm. Yeah, great question. So it's actually if I have an even number. But the question is, well, if I do this, doing this halving thing, and I happen to have an even number of elements, let's just say 4 elements, then the first index is 0, the top index is 3. So what is 3 plus 0 divided by 2? For an integer, 1. So I'm going to actually be setting my middle to 1. That's okay, because if I didn't find it, I'm going to update the pointers anyway. So at worst, what could happen is I examine one more element than I should. But I still will find it if the list is sorted. Okay, it just may take slightly longer. But any questions on the implementation of this? I will post the code of it. Yeah. Great question. So there is a function in the standard library called isSorted that will tell you whether or not the thing is actually sorted or not. But there's no way in the binary search thing, other than just running it yourself, of checking whether it actually is sorted. There's no like property that's in there or anything. Other questions? So let's revisit this point from linear search and binary search, where it says the disadvantage of linear search, it seems, is that it's slow. And binary search's advantage is that it's much more efficient because I'm examining fewer elements with binary search than with linear search. So let's actually test it. So I did some testing this morning. I'll go over the code, but what I found is that these claims are not entirely true. You have to, so sometimes linear search can beat binary search, and we'll see why. So here's the program that I wrote this morning. So you don't have to understand all of this. I'm not testing all of it. I'm just showing you my methodology. So here in this num_int thing, so that's going to be the number of integers in this vector that I'm going to populate in a bit. What I found is that doing this test is almost too fast. So what I did is I'm just going to run this same simulation over and over and over 1,000 times, just so that I get fairer results that way. So this code right here is I'm going to make a vector, and I'm going to populate random integers in some arbitrary order. Okay, so random integers, so I'm not going to get the same run every single time. We haven't covered this function yet, but this actually sorts the vector. So it puts it in ascending order. When we talk about the sorting stuff, we'll get to this, but I wanted to have the same vector when I do linear search versus when I do binary search. Again, so that I get fairer tests. Because if I have a different vector for each one, then I can't necessarily conclude anything. So there's this great header in the C++ library called chrono. So if you want to do high performance and very accurate timing of some code, this would be a header for you. So what I'm doing here is I'm going to start a clock right before each of the tests, and then I'm going to have another clock which indicates right after I'm done with the test, and then I just find out how long it took from the second one minus the first one. So this T1 is the start of the first test. T2 is the end of the first test. And then you don't have to understand how this all works, but this diff at the end is just how many nanoseconds the entire thing took for the first test. And then I print the difference. And then for the second one, I'm going to do T3 and T4, which is for the second test that I print the difference for that test. So the only difference between the two tests is stood find right here. So stood find is a function which does linear search. So you don't have to implement this yourself. Stood find can actually do linear search for you. And since I sorted the vector up here, I can actually do binary search. So there is a function in the library called binary search, which can actually do the binary search for you. So all I'm really doing here is I have 100,000 integers in this vector. I run one test 1,000 times, and that will tell me how long linear search took of a random element. And then I do another test with 1,000 tests of doing it with a binary search way, because the array is in fact sorted. Any questions on how the code works on a high level? So I'm trying to make this a fair test between linear search and binary search. Okay? So let's actually test this. So you don't have to understand how this all works, but if you recall from assignment 4, this O3 parameter, so I just want to make this as efficient as possible. I want to make every optimization that's relevant to these. So I run O3. Oops. Oh, yeah, that's why. So I need to do this to prevent warnings and get the program to work. So if I run this, oops, a.out, then this tells me that it runs, let's see, so that's 39 million nanoseconds for linear search and only 102,000 for binary search for 1,000 random tests. If I make the array even larger, let's compile again and run, then the results are going to be even more striking. So it takes 380 million nanoseconds to run linear versus 200,000 for binary. So it appears that binary search is much faster because at this point, the fact that we're not examining half of the elements on average makes this seem like it runs a lot faster. What do you think I'm going to try next? For a large number of elements, binary search wins. What about a small number? Let's try. Let's put 100 elements in this thing. But maybe because I have such few elements, the number of tests is going to make this kind of a fuzzy result. So maybe I'm going to increase the number of runs in each test. So let's do this. And then, okay, well, now they're a lot closer. So linear is roughly the same amount of work. Let's make it smaller. Hopefully I get the results I got before. Ooh, it's getting closer. Let's do it even shorter. Linear is faster. Even though, no matter what happens, binary search will examine fewer elements on average than linear search, always. It's never the case that binary search will examine more elements on average than linear search. Can anyone know why this happens? Yeah. Well, great question. So the answer, sorry. So the answer was, it seems like binary search is doing more work than necessary. But I'd actually say that's not necessarily true. If we go back to the implementation I had, oops, so I gotta find it, I guess. So if we go back to the implementation here, this divide by 2 makes it seem like it's doing a lot more work, but in fact it isn't, because divide by 2 is actually just a bit shift in memory, and those are fast. The while loop is nothing too surprising there. So I'd actually argue that it's not necessarily the amount of computation here, but it's something else, and it's actually very deep what the true answer is. So the upshot of all this is that you can't necessarily assume the performance of some program or some function versus another, because computers are really complex, compilers are complex, and even different implementations of linear or binary search can make or break one implementation versus another. So what I want you to get away from this is that sometimes linear search is in fact better than binary search on average. And in fact, if I increase the number of tests, hopefully this won't take too long, it's actually significantly faster to do linear search versus binary search. So the only thing I want you to take from this is just think about it. Think about how your code is actually running and actually test it yourself. Because the only way that you could just say, oh, this is true because some very smart person told me this. But in fact, when we really implement it, it's not always true. It's mostly true if I have really large amounts of data, but small amounts of data, the answer is not so clear. Okay? Any question about this? I will put this code up also so that you can play with it. Okay. So that was a fun test I did at 4:30 this morning. So yeah, so I wake up early. All right. So any questions about linear or binary search? If I don't assume that the array is sorted, can I always use binary search? If I don't make that assumption? No, I can't. Because if I'm searching for something that's not necessarily in sorted order, then it may be going to one half of the list, but it's way over here in the other half because the array is not sorted. Okay? So various search algorithms, you have to make some assumptions about whether you can use them or when you can't use them. Binary, you have to have a sorted list unless you can guarantee something about what you're actually searching for. But if you don't make assumptions like that about what you're actually searching for, you can't guarantee anything. You have to have a sorted list. With linear search, you can have whatever. But of course, the world is not just searching for integers all the time. Maybe we're searching for ASU students. So if we have an array of objects, for example, then what could happen is I'm trying to find a student with a particular ID number. Okay? I don't care about any of the other data, about the name or GPA or whatever. I just want the ID number. Then all we need to do is, we could just do linear or binary search as the case may be, but the thing we need to look for is if the array at that index dot get the ID or something, we got to get the ID out of the corresponding student against the thing that I'm checking for. So there's a little bit of a change that you need to do, but it works in the very similar way. So linear and binary search, depending on how the array is, work in very similar fashions. Okay? Any questions about this? About searching? Okay, so now we're going to go into sorting. So nothing on sorting is going to be on the test. Okay? So only up to now, everything on searching may or may not be on the test. So sorting algorithms. So binary search, for the vast majority of instances, is a very good algorithm. It's very fast compared to linear search. So how do we actually sort things, right? So if we need things in sorted order, how do we actually sort them? Okay? Here's a stupid sort algorithm. So I give you a list of numbers, and they're unsorted. You can't guarantee anything about them. Here's what I do. I look at all permutations of that list in every possible order. So for every way to order that list, I look at that list when I flip things around in every possible way. Then for each one of those ways, I look and say, is the array sorted now? Is the array sorted in this configuration, in this one, in this one, in this one? At some point, will I have a sorted list? Yeah, because no matter what happens, if I have some list of numbers, there is some way that they're sorted in some order. Okay? So at some point I will stop, but is that an efficient algorithm? No. So how many permutations are there? Does anyone know? If I have n elements, how many permutations are there? N factorial. So how many of you remember factorial? It's coming back. So the issue is here, if I have even five elements on average, let's just say that I'm looking at all permutations. Well, 5 factorial is 120. So on average, I'll be looking at 60 different permutations in order to get the sorted list, which doesn't sound efficient to me. So we got to think of a more efficient sorting algorithm. Okay? So a sort in general is we got to put the values in some order, either alphabetically. Another sort that might be useful is I want to sort initially by the length of a string. So I have a bunch of strings. I want to order them by a certain length. And for all of the strings of the same length, I want those in alphabetical order. So maybe I have strings of length 5, length 6, and length 7 here. I want all of the length 7 things over here, but I want them in alphabetical order. Then the same thing with the 6s right here, and the things with the length 5 over here. So that's the type of sort we may want to do. So we're going to consider 2 algorithms here, but as you might imagine, there are vast numbers of possible sorts that you could do. So the first one is called bubble sort. So the methodology behind this is we have a bunch of bubbles right here, and then let's just say that, so this is definitely C++, but I'm blowing bubbles right here. What's going to happen with those bubbles usually? Well, pop, but before that. Well, the very light ones are what's going to happen to those, the very small ones. They're going to rise, right? So the light ones are going to rise. What about the bigger ones? They're going to fall, right? Because they have more mass, and for many physics reasons, they're going to fall because they're bigger. Whereas the light ones have a smaller surface area and volume, and then therefore they're going to rise. Although that's not exactly true. I'm not a physicist. Don't hunt me over that. But that's the methodology. Small things are going to rise to the top. Heavy things are going to fall to the bottom. But they don't do this instantaneously. So they're going to start out someplace, and they're going to slowly go up, right? They continuously go up or continuously go down. So they're not going to instantaneously go to the ground or into the stratosphere. So how does bubble sort work in general? I take my list, I look at two elements right here. If they're in the right order, I'm going to leave them exactly as they are. I'm not going to change them because they're in the right order. But suppose that this element is smaller than the first element. What do you think I'm going to do? I'm going to swap them. I'm going to put them in the right order. Okay? So I'm going to look at them like this. I may swap if necessary. So I've looked at the first two. Now I'm going to shift the indices 1 right for both of them. So I look at the second and third elements of the list. Then I do the same thing. Then I do the same thing with the third and fourth and fifth, all the way through. And then if I ever made a switch like this, then I'm going to loop through the list again. If I never made a swap all the way through, what must have happened? They must have been in sorted order. Because I check at each point, are they in fact in sorted order? If they are, I don't touch them. So if I never transpose two elements, then the whole list must be in order. So therefore, we actually finish with that. Okay, so then we keep going until there are no exchanges made. So here's an example. So I have this list right here. Is it in sorted order? No. So let's put it in sorted order. So it says right here, compare 17 and 23. Are 17 and 23 in the right order relative to each other? Yeah. So I don't touch those. Then I move over right one position. I look at the second index 1 and index 2. Are those two elements in the right order? 23 and 5. No, they're not in the right order, so I do a swap. Okay? So I do a swap there. I know 17 and 5 are not in order anymore, but I'm going to return to that because I made a switch early on. But because of this, now I'm going to move right one position again. So I'm going to look at 23 and 11. Are they in the right order? No, they're not in the right order, so I do a swap. And then I've reached the end of the list. Did I make a change some of the way through? Yeah, so now I return to the beginning of the list and go again. So this is the list we had before. We look at 17 and 5. They're not in the right order, so I do a swap. So then after that, because I made a swap there, I'm going to return to the list at the end again. But we're going to look at, so we did that. Now we move over one index again. We look at 17 and 11. They're not in the right order, so I do a swap. So we made a swap. Then we look at 17 and 23. They are in the right order, so I don't make a swap. Should I go back to the beginning of the list? Yes, because I made a swap earlier on. So I go back. We go back. We look at 5 and 11. They are in the right order, no change. 11 and 17, no change. 17 and 23, no change. We reach the end of the list. Is the array sorted? Yeah. So in fact, now the array is sorted. Okay? So think about what's actually happening here. So the light element, say the 5 here, is floating down to the beginning of the list, and the heavy elements, 17 and 23, are floating to the top of the list. Okay? So that's the basic methodology for bubble sort. So the great thing is that it's super easy to implement because all you do is you have a bool condition to say, did we actually make a change along the way through? And then while we made a change, iterate through the entire thing. So we'll do a demo next time. So we look through each of the elements in the list, and then we just do a comparison. If we need to make a swap, do a swap. And then we just keep going until the entire thing is done. But we'll do it next time. It says that it's inefficient. Should you think that this is always inefficient? No, so by my earlier demo. So think about this and implement it yourself. I recommend it. I'll see you all on Wednesday.